Hello, my name is Jeff Mann, and I'd like to give you my thoughts on quantum physics. Quantum physics is a strange world because the particles are too small and they're moving too fast for anyone to see. So the whole world of quantum physics is a black box, and no one can see inside. So what scientists do is they put something in one side, they see what comes out the other side, and then they take a guess as to what's inside the box. One of the more popular guesses is the probability function. I'd like to talk about that more in just a couple of minutes. We live in a four-dimensional universe, 3 dimensions of space and 1 dimension of time. Mass warp space and energy is related to mass equals mc squared. So energy is related to mass, is related to space, is related to time, and they're all interrelated. One day I had a thought. That thought was, what if there was a link here? If mass warps space, what if energy warps time? So I thought about what does that mean? And if you imagine planets going around stars, you could imagine swirls of time going around each of these little particles. Every particle has its own clock. The more energy a particle has, the faster that clock would spin. So here's a particle, and we have swirls of time going around each particle. The interesting thing is that time is moving backwards and time is moving forwards. So each particle, again, has its own clock. Now, where this becomes interesting is if you look at spin. Spin is a change in angle divided by the change in time. The variable here, though, is time. Time is going every which direction. So if we look at it, here we have time moving its slowest, and here time is moving its slowest. So at the smallest denominator, you have the most spin here, and the most spin here on this drawing. Where time is moving its fastest, which is here and here, we have the largest denominator, we have no spin, here and here. So when time is spinning quickly, the particle will behave like a tornado or like a particle. So here it's a particle, and here it's a particle. And where it's no spin, it behaves like wind or a wave. So this would be a wave here and a wave here. So each particle is transitioning between particle wave at the frequency of the particle. So each particle has a frequency. One particle wave transition would be the frequency of the particle. Now, if we look at a laser, we have particle, wave, particle, wave, and if we place mirrors an exact multiple of wavelengths apart, then the particles will bounce off the mirror. Particle, wave, particle, wave, and the particles will bounce back and forth without ever interfering with each other. If we vary the mirrors by any distance, the particles will always collide. Now I want to look at the probability function. The probability function says that these particles travel as large clouds of probability, not as particles. The problem with that is that it doesn't fit well with general relativity and doesn't fit with the Bohr model of the atom. If these clouds of probability are thousands of atoms across, it would be difficult to associate an electron with any particular atom, much less any particular shell within the atom. And every time it's measured, it shows up as a particle. So there's some issues there. And the reality is nobody actually believes that because probability can be tested. And the probability function has never been tested in 100 years. And that's because everybody really believes it's magic. But you can test it this way. Probability function is drawn as a bell-shaped curve. Using quantum tunneling, if I had a barrier this thick, the probability on the right is the percentage of particles that should get through. So I could measure that, and I could plot that. If I had a thicker barrier, and a thicker barrier, etc., I could plot that, and if the probability function is correct, you get a curve that looks like this. If I'm correct, however, you're going to get a straight line. This would be the thickness of the barrier and the percentage of the particles that get through. And this is a test that really needs to be run. It's 100 years overdue. Nobody's ever tested this. And a lot of scientists, including Einstein, didn't like it at all. I, unfortunately, do not have the means to test this. But if anybody does, you can reach me. My email address is jeffjames85 at gmail.com. I would be glad to have your help on this matter. If you can do this, please let me know. Now, I ran into a problem with this because if the particle is quantum tunneling and it comes up to the nucleus of an atom, it'll split to go around the atom. And it will see another atom, another nucleus, and another nucleus. And when it gets to the other side, it should be a mess. But it always shows up as a particle, and that's a problem. It does not instantly collapse into a particle when you look at it. That's just an attempt to explain something they couldn't explain otherwise. So I thought about this for a while, and I figured that out. What happens is, any particle with mass, electron, proton, neutron, the nucleus of an atom, a black hole, the energy from the Big Bang, all warp space such that the space around it is zero. They're all singularities. But they all have a diameter, and that diameter is the amount of space that's missing. So then, when the particle hits the nucleus of an atom, it goes around it. When it gets to the other side, it's in the same place. So it goes on unaffected. So that's why it will always be a particle. This is a provable point. The way to prove this is with an entangled pair of particles. If they travel the same distance, they'll get to the end at the same time. If I put a barrier in front of one of the beams, the particles tunneling through that barrier will travel a shorter distance than the ones going through empty space, and they will always arrive at the end sooner than the particles going through empty space. I think this is known already, but the difference in time is the number of nuclei the particle passes through times the diameter of the nuclei divided by c. And that would be the difference in time when they reach the other side. So this can be measured. This is measurable as well. Again, I do not have the means to do that. If you do, I would be glad to have your help in this area. Now, where this is huge is actually for astronomy. One of the popular ideas about astronomy is that shortly after the Big Bang, a large volume of space was instantly created. That large volume of space was not instantly created. It was the missing space that popped back. So that is goes along with that theory, sort of supports that theory, but it also means that our Big Bang did not create time and space. It's always been and always will be. And so with infinite time and infinite space, we're not the only Big Bang. Whether they occur infinitely far apart or if they overlap like fireworks, I don't know. But again, this is something else that needs to be tested. Now, this is my favorite part about this, and that is when you look at nuclear magnetic resonance. With time moving around, going forward and backwards, each particle that has a charge, in my case I like protons because I have 8 years of MRI experience, but the charge on that particle will go like this and go like that. It will be oscillating back and forth. Because of that, if you put it in a magnetic field, It precesses at the Larmor frequency, which we know is true. And half tend to align with the magnetic field and half tend to align against the magnetic field, which we know. There's no such thing as magically lining up with the magnetic field or spin up or spin down. Again, that's something that was thought of in the 1920s, but nuclear magnetic resonance resolved that problem in the 40s, and nobody's let it drop since then. So these are my thoughts on quantum physics. Again, if anybody has the means to run these two tests, am I right or am I wrong? Is the probability function correct, or is it none of the above? If you have the ability to run those tests, please let me know. My email address is jeffjames85@gmail.com. Thanks.